Hello, I'm Andre Araujo, a PhD student in the Department of Electrical Engineering at Stanford University. This video presents a summary of the main contributions in my thesis, which is entitled Large-Scale Video Retrieval Using Image Queries. We live in an era where vast amounts of data are collected from us and from everything around us at an astonishing pace. Most of these data are in the form of multimedia content. Today, it's estimated that around 85% of the web is multimedia. Multimedia is called the dark matter of the digital age. Today, more than 400 hours of video are uploaded to YouTube every minute. Facebook users generate more than 8 billion video views per day. Nest reports more than 100 hours of surveillance video uploaded per minute. A fundamental challenge today is to make sense of these data. These data show what's going on with us on a personal level and what's going on with society as well. To try to understand these data, researchers have explored automatic visual recognition. Considering this image of a busy scene, researchers have addressed different recognition problems. For example, in image classification, techniques were developed to answer questions such as, is this an urban landscape? In object detection, a system would try to recognize objects, for example a bus, and accurately locate them. Another example is the problem of instance recognition or visual search, where we are trying to recognize a specific instance of an object, for example a specific billboard instead of any billboard. This is by no means an exhaustive list. Many other recognition problems exist, for example activity recognition, pose estimation, etc. The visual search problem gained substantial popularity recently. In the example shown here, the user queries the image on the left to obtain information about a CD. The database of images on the right contains reference images for all objects that the system can recognize. This type of technology can be used to recognize products and locations, for example, and has also been applied to several commercial applications. In this work, in my thesis, I'm interested in an extension of this visual search problem where the database is instead composed of video clips. There are several applications for this type of technology. For example, brand monitoring, content linking, online education, and many others. To illustrate this application, we put together a prototype which works in real time and can be accessed online. For example, by clicking on the image shown on the website, the system presents all matches with videos in our database. Note that the system recognizes that these images are similar even with significant changes in viewpoint or lighting. The user can then play the video from the point where the image was found. The system also allows searching with your favorite image. In this example, the user copies the URL of a specific logo image and enters that into the system. In real time, the system fetches the image, extracts descriptors, and searches the video database. Note how the matches are quite challenging due to occlusion and different viewpoints. Once again, the user can then play the video from the point where the match was found. I told you that visual search with a database of images is well developed, so you might be wondering if we could search a video database by simply considering each database video frame. In this slide, let's consider the architecture of a system which does exactly that. First, we extract a descriptor for the query image, which is used to compare the query against frames in the database. At this point, we obtain a short list of frames which are to some extent similar to the query image. Then this list is re-ranked by using feature matching and geometric verification. The final result consists of video frames which are very likely similar to the query image. The main building blocks in this architecture have been very well studied in the last decade. The problem, though, is that in practice, video databases are very large, so methods that compare the query directly to video frames do not scale. In this work, I propose a new retrieval architecture, which I argue is more suitable for large-scale problems. I introduced a new retrieval stage where the query is compared directly against video clips in the database. In subsequent stages, we only consider a small number of video clips. Our goal is to very efficiently narrow down the retrieval process to the most promising video clips. This stage is the focus of this work. This is the first comprehensive work to address retrieval of video clips using query images. This problem presents mainly two challenges. First, we need to figure out how to compare images to videos, which is an asymmetric problem since videos have a temporal component and the query images do not. Second, to build a descriptor for a video clip, we need to find some way of aggregating all of the information of the video clip into a compact descriptor. These challenges are directly related to my main contributions. My first contribution is a technique to perform Fisher vector comparisons in an asymmetric way. Fisher vectors are image signatures that I will introduce in one of the next slides. The technique that I propose handles image matching when the query or database is cluttered, providing substantial retrieval quality gain. My second main contribution extends Fisher vector descriptors to video segments. Such descriptors enable efficient large-scale retrieval for many types of datasets. Finally, in my third contribution, I propose a different method to construct descriptors for video segments. This technique is based on Bloom filters and enables fast and accurate retrieval for many datasets. In this talk, I also review the concept of Bloom filters, which is important for this contribution to be well understood. Before discussing my contributions, it's important to review related work. The visual search problem can be performed with different types of query and database information. As query, one can use an image or a video, and in the database, one can also have images or videos. The most common visual search problem refers to searching the database of images using a query image. Important work in this area includes the SIF descriptor, bag-of-words model, and Fisher vectors. When the query is a video and the database contains images, one can augment query videos using information about the retrieved image. In this area, recent work has focused on compressing local and global descriptors efficiently using temporal information. When the query is a video and the database is composed of videos, the most common application is content tracking. Recent work includes schemes that match frames and check for spatial temporal consistency, as well as the TrackVid copy detection challenge. Our focus is on the video retrieval by image problem, discussed on the next slide. Early work in this area explored small databases composed of one or a few movies. The bag-of-words model, which is very popular for searching image databases, was actually initially introduced to search a database of videos by Sivich and Zisserman. In subsequent work, Sivich et al. Were able to track objects in multiple scenes and allow object-level retrieval, where a query with a specific view would retrieve the object under any view. Video retrieval by image gained popularity with the introduction of the TrackVid Instant Search Challenge in 2010. TrackVid is a workshop organized by the National Institute of Standards and Technology, where a common dataset is provided to research teams and performance is compared on different video retrieval tasks. The Instant Search Challenge refers to searching a video database using multiple query images with the objective of finding relevant shots. The highest performing system in 2010 and 2011 by Lee et al. Used the frame-based indexing approach with color sift features. Later, Zhu et al. And Ballas et al. Reported improved performance when features were aggregated over shots using the bag-of-words technique. Another interesting technique introduced in this workshop by Zhu et al. Concerned the use of query adaptive dissimilarities for bag-of-words. More recent work in this area has focused on the problem of object localization in videos. Apostolides et al. Studied the use of surf-based matching per shot, and Meng et al. Proposed to use a dynamic programming solution for this task. Now let's review some background such that my contributions can be well understood. Consider matching these two images and consider initially the query image on the left. First, we perform interest point detection to find salient image features such as corners or blobs. In this work, I used the state-of-the-art hash-unifying detector. These features are described by local image descriptors. In this work, I used the standard SIF descriptors. These descriptors can be seen as points in a high-dimensional space. They are illustrated here in 2 dimensions, while they are usually of much higher dimensionality. The same process can be repeated for the database image to obtain key points and descriptors in red. Descriptor matching then happens by finding descriptors from the query image which are similar to descriptors from the database image. For example, the descriptors circled here could be considered matches. This process works very well, but when the database of images is large, we cannot afford to use pairwise matching since there are too many images in the database. To address this problem, several techniques were introduced, and one of them is a state-of-the-art technique called Fisher vector. A key property of Fisher vectors is that they can represent a set of descriptors by a compact fixed-length vector. As a consequence, 2 images can be compared by comparing their Fisher vectors. The Fisher vector arises by describing an image with the aggregated Fisher scores of local descriptors. The distribution of image descriptors is modeled using a Gaussian mixture model, and usually only the Gaussian means are taken into account. This technique can also be seen as an extension of the bag-of-words method. In this slide, I'll present the basic way a Fisher vector is constructed. First, in descriptor space, a Gaussian mixture model is trained using features from training images. Consider the construction of the Fisher vector for the query image with descriptors shown in blue. The Fisher vector is a vector of total size given by the number of Gaussians, in this case 3, times the number of descriptor dimensions, in this case 2. So in the star example, it's a vector with 6 dimensions, with all entries initialized to 0. Each 2-dimensional chunk corresponds to the residual for a different Gaussian. Consider the Gaussian on the left. We first obtain the residuals of each descriptor with respect to the Gaussian mean. The residuals are then scaled by their soft assignment with respect to this Gaussian and by the covariance structure of this Gaussian. Then we obtain their average, which composes the 2 dimensions corresponding to this Gaussian. The same process can be repeated for other Gaussians and the initial Fisher vector is obtained. The final query Fisher vector is obtained after L2 normalization. The same process can be repeated for the database images, obtaining 1 Fisher vector for each database image. To compare the query image to a database image, we can now simply compare their Fisher vectors. More recently, it's been shown that Fisher vectors can be made more compact by using component-wise sign binarization, with very little loss in performance. We denote such binarized Fisher vectors as FV star in the rest of the talk. Now I'll introduce my first contribution, asymmetric comparisons for Fisher vectors. Consider the pair of images shown in this slide. These images have similar contents, the Time magazine cover, but the image on the right contains other visual information, such as the text overlay or the content on the background. In this case, this pair of images presents asymmetry. The image on the left is contained in the image on the right, but not the other way around. This asymmetry is even more pronounced when we are comparing an image to a video, so everything I discuss here can be directly applied to the video retrieval by image problem. This pair of images is common in an object retrieval application, where we want to test if the image of the object on the left is contained in a database image. Another asymmetric example would involve this other pair of images, which could occur in a video bookmarking application. In this case, the query photo on the left must retrieve the database video frame on the right. For example, a user could use this to resume playback of the video she was watching. In this case, note that the asymmetry is reversed. This type of comparison is not directly supported when using Fisher vectors. Fisher vectors are commonly used to test if 2 images are similar in general, but they do not directly support testing if one image is contained in the other. The goal of my first contribution is to design an asymmetric comparison technique for Fisher vectors. Let's now consider this problem in more detail. First, remember that the Fisher vector for an image is a concatenation of residuals for the different Gaussians. I denote each residual here by lowercase v. We know that each of these residuals correspond to some type of feature found in the image. I illustrate these different types of features using the shapes shown here. Consider again this pair of images we want to match. We can highlight the portion of the images that should match in orange and the clutter region in blue. Usually the blue and the orange regions have very different statistics, and more specifically, the features from the blue region are usually not present in the orange region. We can illustrate this problem in 3 dimensions as follows. Consider the simplified case where each component corresponds to a different type of feature, x, y, or z. Each component in practice would correspond to a different Gaussian in the Fisher vector. First, remember that the comparison metric for Fisher vectors is cosine similarity, since Fisher vectors are L2 normalized. In other words, we want the angle between corresponding images to be as small as possible. Say the blue vector Q corresponds to the query vector containing only visual patterns like x and y, not containing z. So it's a vector that lives on the xy plane. You can think of it as the query image in the previous slide, which contains some types of features but not others. Say the green vector M corresponds to a correct matching image in the database that contains a significant amount of x and y, but also of z. You can think of it as the database image in the previous slide. Denote M' the projection of M to the xy plane. Finally, consider the red vector N, which corresponds to a non-matching image, which randomly contains features reasonably similar to the query and lives in the xy plane. Denote θ1 the angle between Q and M, θ2 the angle between Q and N, and θ1' the angle between Q and M'. We would like to have θ1 lower than θ2, as in this case the vector Q would be closest to the correct matching vector M. In this example, however, we get a common failure case. θ1 is greater than θ2, so we don't get what we wanted initially, but at the same time, θ1' is lower than θ2. This leads to the insight that we should compare query and database items based on their projections to the xy plane. In practice, that means that we should use only Gaussians visited by the query. To decide if we should use a Gaussian residual or not, we use the technique described as follows. Consider the Fisher vector for this image illustrated here. We can see from the illustration that all descriptors are far from the Gaussian on the bottom right. That means that this Gaussian is not visited by this image. In practice, we measure the soft number of descriptors assigned to this Gaussian. In this case, we discard the information from this Gaussian by setting their components to 0 and renormalizing the entire vector. This defines the projection I mentioned in the previous slide. What I presented so far was the intuition on how to compare 2 images when we know one is supposed to be contained in the other, and how to select the projection that defines the comparison. Using those ideas, I considered 2 different asymmetric problems. First, the case where the query might be contained in some database image. In this case, the query defines which components of the Fisher vector will be taken into account, and all database images are compared to the query based on the same projection. This works really well in practice. In the second case, I considered the application where the query might contain one of the database images. For the comparison of a query database pair, the database image now defines which residuals of the Fisher vector are taken into account. This is a problem since each database image will have different types of features, and as a consequence, each comparison is done based on a different projection. If we apply the technique presented here directly to this retrieval problem, this does not work at all. The solution to this problem is the introduction of a weight that favors database images with more visited Gaussians. This penalizes database images with small amount of information, and as a result, the system works well. I won't go in detail here on this technique in the interest of time. Since this problem has not been studied in detail before, I created my own datasets. First, consider the case where the query is contained in the database. We consider 200 query images with their corresponding correct matches in the database. We add a set of distractors, making for a database with 10,000 images. And we're interested in observing the importance of asymmetric comparisons for different amounts of clutter. So we add from 0 to 40 images to each database image and evaluate the performance for each of these different cases. When I say that images are added here, I mean that the features from all images are pulled together and one Fisher vector is extracted for the set of images. This simulates having images with more clutter or the aggregation of several images together. In the other configuration, the asymmetry is reversed. In this case, we add clutter to the query images and we use a dataset of similar size. In the experiments, the objective is that each query retrieve the correct database image. In this slide, I show experimental results using 2048 Gaussians in the Fisher vector. On the left, I show results for the case where the query is contained on the database, and on the right, I show results for the case where the database is contained in the query. The x-axis shows the number of clutter images added to each database image, and the y-axis shows mean average precision, which is a retrieval quality measure where higher is better. The black curves show the baseline scheme that simply compares two Fisher vectors directly, and the curves with other colors present the asymmetric schemes in the two cases. The solid lines show the performance of the Fisher vector technique, while the dashed lines show the performance of binarized Fisher vectors. The asymmetric schemes outperform the baseline by up to 25% in both cases, so the proposed technique works very well. Next, I'll walk you through my second contribution, temporal aggregation using Fisher vectors. Once again, this is the large-scale architecture of the retrieval system I consider. The main focus of this work is the stage highlighted in this slide. In this contribution and the next, the objective is to design efficient video clip descriptors that can be compared directly against query images. To study the design of descriptors for video clips, it's important to take a step back and consider how videos are naturally structured. A video is an ordered set of frames, and in our application we consider frames extracted at 1 frame per second. Frames can be grouped into shots, which are video segments within 2 cuts. Shots naturally contain similar frames, and their length is on the order of seconds. In my thesis, I provide a thorough experimental evaluation of shot aggregation techniques using Fisher vectors. I won't discuss this here in the interest of time. Shots can be grouped into video clips, which are segments of video with length on the order of minutes, containing diverse shots. For example, YouTube video clips are 4 minutes long on average. For longer video content, for example a 30-minute newscast, we could use a technique called scene segmentation to generate clips like these. This is the first work that considers aggregation over such long clips in order to match against a query image. In the next slides, I'll present some of the different aggregation techniques that I introduce in this work. The first and most straightforward aggregation technique I propose directly extracts a Fisher vector from all features within a video clip. First, we extract local features from each frame independently. Then, all features are aggregated together in a clip Fisher vector. The second technique I introduce attempts to reduce temporal redundancy before Fisher aggregation. This is related to previous work which showed that aggregation of similar features over an image might boost image retrieval performance. To experiment with that, we start by extracting local descriptors from each frame independently, as before. Then, the features are tracked over the clip such that we know which of them presents similar visual information. Finally, we construct aggregated descriptors by averaging the original ones and renormalizing them. We can then construct a clip Fisher vector using aggregated descriptors. I call this a clip Fisher vector with tracked features, or clip FVTF for short. The last variant that I present here considers clip-based aggregation after Fisher aggregation is performed in the first stage. We again start by extracting local descriptors from video frames independently. Then we perform Fisher aggregation over shots, and the final clip descriptor is constructed by averaging shot Fisher vectors. For the experiments, I consider 3 datasets. First, a dataset composed of news videos with query images collected from the web. This is the largest existing dataset for this research problem. The video clips in this case are on average 2.7 minutes long. I consider 2 versions of this dataset, one with 600,000 frames, 164 hours of video, and 3.4 thousand clips, and the other one for large-scale experiments with more than 1,000 hours of video, 4 million frames, and 24,000 video clips. Second, the video bookmarking dataset, which considers the application where the user takes a photo of a display to resume playback of a specific video. The database videos are the same as in the news videos dataset, but now the queries are very different as shown here. Finally, I consider a dataset of lecture videos collected from Stanford's courses. The database consists of lecture segments with average length of 8.2 minutes. The queries depict clean images of slides that are presented during the lectures. We use similar versions of this dataset. Note how these 3 datasets present very different characteristics. The news videos and video bookmarking datasets present much more varied contents than the lectures dataset. In the lecture dataset, the matching object covers the entire query image, while this is not usually the case for the other datasets. Throughout the talk, the experiments considered the versions of the dataset containing 600,000 frames, and at the end of the talk I present large-scale results. In this slide I present a comparison of the different clip descriptors for the different datasets using 512 Gaussians and asymmetric comparisons. In this type of experiment, the result is a ranked list of video clips. You can see that the average shot Fisher vector technique in yellow performs poorly, while the clip Fisher vector and the clip Fisher vector with tracked features perform similarly. This shows that aggregation of local features before Fisher aggregation is not very important. Now consider the lecture videos dataset. This plot presents clip Fisher vector results using 2 different comparison schemes as a function of the number of Gaussians in the Fisher vector. In red, I present the asymmetric technique introduced in this work, and in black, the standard Fisher vector scoring. Asymmetric comparisons are very important for this application, with improvement of 30% mean average precision. This plot also shows how retrieval quality improves as you increase the number of Gaussians up to 2048. Note that this is much higher than what is commonly used for frame Fisher vectors. This plot presents the main takeaway for this contribution. Here I plot mean average precision as a function of the index size. We compare clip Fisher vectors in red with the baseline frame Fisher vectors in magenta. The 2 curves are constructed by varying the number of Gaussians in the Fisher vector. This plot shows that clip Fisher vectors work very well for this dataset. We obtain 2 orders of magnitude database savings with the same mean average precision. For other datasets, however, the results are not as good. In the video bookmarking dataset, we construct a 43 times smaller index, but this time there's a mean average precision drop of 26%. The situation is similar for the news videos dataset. So the conclusion from this part is that clip Fisher vectors generate very compact databases, but their effectiveness depends on the type of data under consideration. The goal of my next contribution is to find a new aggregation technique that can be effective for different types of data. My third contribution uses Bloom filters to construct descriptors for video segments. But first, let's take a step back to consider the problem from a different perspective. Consider the Gaussian mixture model of the Fisher vector in the descriptor space, and let's zoom into a particular Gaussian. When we aggregate descriptors over a frame, some descriptors in that frame will have large residuals like the ones shown here. When we aggregate over a video clip with the same number of Gaussians, several frames will have residuals with large magnitude. Each frame is denoted here with a different color. At this point, if we simply average all residuals, they end up mixed together too much, losing discriminative power. To fix this problem and construct an effective descriptor for a video clip, there are several possibilities. The first one is the contribution I just introduced. Using a clip Fisher vector, we increase the number of Gaussians, which reduces the interferences between residuals. But we can also explore other types of aggregation. In particular, I consider techniques that make use of hashing, which has been successfully applied to several research problems. One option I consider is to first aggregate per frame in a Fisher vector. Here, each dashed vector represents the aggregation over a frame. Then aggregate temporally by embedding them in a high-dimensional space using hashing. Another option is to simply perform spatial-temporal aggregation by hashing the residuals directly. In this part of the talk, I'll introduce a flexible technique based on Bloom filters that enables us to experiment with the second and third aggregation methods shown here. In this slide, I'll introduce the Bloom filter framework with an example. In the interest of time, I will illustrate only one variant of Bloom filters. A Bloom filter is a data structure that represents a set using a compact signature. Say that we want to describe the set S, which contains the items D1, D2, and D3 shown here. Bloom filters are bit vectors. On the left, I show a Bloom filter with two partitions, which are initialized with zeros. Here's one of the hash functions for this toy example in red. In this case, all elements within each of these slabs are hashed to the same value. Let's start by hashing D1 into the Bloom filter. D1 is hashed to bucket 6, so we set that element to 1 in the Bloom filter as done here. Next, consider D2, which is hashed to 2, and then bit 2 is set. And finally, consider D3, which is hashed to 6, but that bit was already set to 1, so it does not change. The same thing happened when using other hash functions. We set to 1 the buckets where the items fall, and in this case we used the second partition. Now we're interested in querying items against the Bloom filter. We want to know if the query item is similar to an item from the set S. Consider Q1, which is close to D1, so we expect the Bloom filter to respond with many matches. And indeed, it's the case here. Q1 is hashed to 6 and 5, and these locations are 1 in both cases. So the Bloom filter responds with 2 matches, and this is a true positive. Unfortunately, false positives may also arise, such as when querying Q2. It's hashed to 2 and 7, so the Bloom filter responds with 2 matches. This is a false positive because the Bloom filters respond with many matches, even if Q2 is far from all elements in the set. This toy example gives you an idea of how Bloom filters are used for indexing and querying. Now, let's consider how Bloom filters can be applied to my problem. In the method described in this slide, we start by extracting frames from video clips and local features for each frame as before. Each frame is then encoded as a Fisher vector in the exact same way a Fisher vector is extracted for an image. We first embed local features into the Fisher space and then aggregate them per frame. The Fisher vectors are then hashed into a Bloom filter. I call this architecture BFGD since global descriptors such as Fisher vectors are hashed into Bloom filters. In this slide, I present a different method that uses a similar architecture. The only difference with respect to the previous slide is the lack of aggregation per frame. This leads to what is called a point-indexed representation, where each feature is encoded separately. The embedded features are hashed directly into the Bloom filter. I call this architecture BFPI since a point-indexed representation is used. Now let's consider which hash functions to use. In this work, I consider random functions using locality-sensitive hashing and quantizer-based hashes. I consider locality-sensitive hashes that work by projecting to random hyperplanes followed by sign binarization. In this case, to get n bits, we need n random hyperplanes. On the right, I show quantizer-based hashes. These are trained using approximate k-means, which uses approximate nearest neighbors to speed up vector quantization. In this case, the number of bits we get is equal to the log of the number of centroids. I initially present experimental results on the news videos dataset. We use Fisher vectors with 512 Gaussians, and we set the number of hash functions also to 512, since this works well in practice. This plot compares BFGD to BFPI using LSH. This plot shows mean average precision as a function of the number of bits per hash. For a large number of bits per hash, the matches are very discriminative. For a small number of bits per hash, the matches are more invariant. So usually there's a trade-off between these two to obtain the optimal number of bits per hash. This plot shows that BFPI is much better than BFGD, which indicates that it's better not to aggregate descriptors per frame before hashing. This plot shows results for BFPI comparing different types of hashes. We can see that quantizer-based hashes perform better than LSH. In this bar chart, I present a comparison of the two proposed techniques on all datasets. We clearly see two trends. The Bloom filter performance in blue decreases as we move from the news dataset to the lectures dataset. The trend is reversed for the Clip-Fisher vectors in yellow. This happens due to the nature of these datasets and techniques. For the news dataset, the matches are essentially local, for example, when we match objects in cluttered images. In this case, the BFPI technique works well because residuals for local descriptors are hashed directly, avoiding too much aggregation. On the other hand, the matches for the lectures dataset happen when the entire query image matches to almost the entire frame. In this case, Clip-Fisher vectors tend to work well because they consider aggregated descriptors. The video bookmarking dataset is in between. Finally, I present large-scale results where we make use of inverted index structures for efficient retrieval. For Bloom filters and Clip-Fisher vectors, the top clip results are re-ranked using shot Fisher vectors. Here's the results for the news videos dataset. Frame Fisher vector results are presented in black for a comparison. The Bloom filter scheme achieves similar MAP to frame Fisher vectors with substantial savings in latency and memory. The Clip-Fisher vector scheme is better than the other schemes in terms of the index size, but its mean average precision is low in this case. For the lecture videos dataset, the Bloom filter results are also very good, with high MAP, low latency, and low memory. The Clip-Fisher vector results are very good for this dataset. High MAP, latency comparable to Bloom filters, and very low memory footprint. In this work, I first introduced asymmetric comparisons for Fisher vectors, which work by projecting vectors of cluttered images into a subspace. I studied two asymmetric retrieval problems and showed large retrieval quality gain in both cases. Then, I proposed Fisher vector descriptors for video segments. I compared several types of aggregation, showing that a simple aggregation technique performs as well or better than other techniques. For a dataset of lecture videos, the proposed technique enables high-quality retrieval with 100 times less memory than a frame-based technique. Finally, I proposed a Bloom filter aggregation technique which enables different types of spatial temporal aggregation. I studied the choice of hash functions and showed that the best configuration achieves high performance in 3 datasets while being much faster and lighter than a frame-based technique.